All right, so here we are at the modified Atwoods machine lab. Okay, so if you look at, click this button right here, we can select the system mass, which is a combination of the hanging mass plus the mass on the track and the hanging mass. You don't want the hanging mass to be 0, or else it won't go anywhere. I'm going to do the experiment for um, a 500 gram system mass. Let's hit load. Okay. Now, if you scroll down, I'm going to jump ahead a little bit. It says design, in step 2, design an experiment to determine the relationship between the acceleration of the system, that's the track and the hanging mass together with a string, and the accelerating force applied to the system. So the accelerating force applied to the system, that when we model those forces on the Atwoods machine today, and the only force that's accelerating the system is the gravitational force acting on the hanging mass. Okay, so we can modify that force, and as a result, the acceleration of the system changes. Okay. Now, what we're going to keep constant is the system mass. So believe it or not, right now the hanging mass is 40 grams and the system mass is 500 grams. What that means is that it's 500 total, so the mass on the track is 460 grams. If I change this to 60 grams hanging, notice the system mass is still 500. Well, now the mass on the track is 440. Well, so together they equal 500. So as you increase the hanging mass, the mass on the track decreases in order to keep the system mass the same. The reason why the lab is set up this way is because if you consider the equation F equals ma, if we're graphing F force versus A acceleration, we have to hold m constant. We have to hold the mass constant, in this case the mass of the system, because we're studying the acceleration of the system. Okay, so let's go ahead. I'm going to go through the whole lab. Feel free to skip ahead, different parts, especially the data collection part, but you might want to see how I set it up. All right, so I'm going to set up my tools, get my meter stick. I'm going to set it right at the front of the mass on the track, and then I'll press play. And I want to go back to the moment when I can see that the string is cut. So I'm going to go frame by frame. Okay, I can see it's cut right there. Now I'll reset my clock and start collecting data. So I'm going to just measure how long it takes to go 30 centimeters. So I'm going to press play. I'm going to go a little bit further and show you it would be bad if I went all the way to here, because the mass has already hit the ground, right? And that's a different scenario. There's no longer have a system that's just being accelerated by the force of gravity on the hanging mass. So let's go back. So I'm about 39 centimeters or so. So I'm just going to try to go 30 centimeters each time. So I'm going to go frame by frame or drag till I'm at about 30 centimeters. Okay, so it looks like it took 0.7208 seconds to travel 30 centimeters. So first thing I'm going to measure is displacement, or record displacement measured in meters, variable d, and I'm going to convert centimeters to meters in my head. So it went 30 centimeters. That's 0.30 meters. And then I'm going to record how much time it took. Units seconds, variable t. Okay, and that was 0.7208. 0.7208 seconds. Now, with the displacement in time, I can figure out the acceleration. All right. So what I'm doing here is I'm going to rearrange the equation for displacement on the right. And I'm going to measure that in meters per second squared. Variables A. Now I'm going to use a formula to do this. Now if we know it's starting from rest, and we take our delta x equals v naught t plus 1/2 at squared equation, we can rearrange it to get acceleration equals 2 times delta x divided by t squared. So I'm going to insert a column formula, and I'm going to say 2 times the displacement divided by parentheses time squared. All right, so again, that's just rearranging the kinematics equation to solve for acceleration if you know displacement and time, and if you are starting from zero velocity, so the v naught t part of the equation disappears. And it automatically calculates my acceleration. Great. Now, I also need to record information about the system that I had. So I'm going to hanging mass, and my units are, I want it to be kilograms. So I'm going to take the hanging mass and divide by 1,000. So that would be 0.060. And that's M mass hanging, MH. Okay. Now we're going to turn that into a force, right? Force of gravity on the mass hanging. So that's our force of acceleration. Force of gravity, H, of the mass hanging. Units, okay, are going to be newtons. And the variable, we'll say F. And we can make a formula for this one too. We can just take the mass hanging and multiply by 9.81 meters per second squared. All right, so that's mg, and that'll give us newtons, right? F equals mg. So now I can do my graph of force or acceleration as a function of force. Just need more data. So let's come back here. So right now, this was hanging mass of 60. Let's change it down to 20. Load it up. Okay, let's go frame by frame until the string gets cut. All right, it's clearly cut right there. I'll reset my timer, and we're going to go 30 centimeters. It's taking a lot longer because there's not as much mass hanging. All right, see, it took 1.2417 seconds. You know what? I don't know if I reset my timer. Let's try that again. All right. Yep, I did reset my timer. Sorry, starting at 0. And 1.2417. 1.2417. So this is 0.3, that's 30 centimeters, 1.2417 seconds. Acceleration gets calculated automatically. The hanging mass was 0.02, so my hanging force was 0.196. All right, let's change it again. So just to be clear, my the mass on the track was 480 grams, right? Because 480 plus 20 is 500. Okay. Now the hanging mass is 40 grams. Mass on the track is 460. All right, string is cut. Reset the timer. Press play. I'm going to travel 30 centimeters. .8792. 0.8792 seconds to travel 30 centimeters, which is 0.3 meters. There's my acceleration. My mass was 40 grams, or 0.040 kilograms. There you go. There's my force. Okay. Now the hanging mass is 80 grams, and the mass on the track is 420. Okay, reset the timer, let it run. Again, don't stress too much about being exact, but try to be somewhat precise with your data. All right, 0.6208. 0.6208. Notice the order doesn't matter, right? I didn't go from least to greatest in terms of the hanging masses. When you graph it, all the points go to the right spot, right? So it doesn't really matter. So this was 0.080, and there's one more. Now the hanging mass is 100 grams, and the mass on the track is 400 grams. So let's see if we can figure out where it got cut. All right, reset. Press play. Now, if you have any data points that don't look good, you can always go back. All right, you can always go back. Like right here, this data, I'm getting 0.8583. 0.8583. That doesn't seem to make sense to me. 0.8583. Just by looking at, seems like this should be the shortest amount of time because I had the most mass, right? Oh, this is the video where there's a mistake. If you look closely in the video, on the pulley wheel, the string has fallen off the wheel. So this is this is a special case where that data point's not going to line up, and we're going to have to exclude it. So that's kind of tricky. I think this was a special case. I don't think this happened very often, but I'm glad I chose the case where it did happen. So let's go ahead and graph our data now. Acceleration as a function of the force. So we're going to choose acceleration on the y-axis, no uncertainty, as a function of the force. And we get really good data points with the exception of this one. So we'll turn it off. All right, that was that one where it actually came off the wheel, believe it or not. So let's do a curve fit. Looks pretty proportional. Let's hit done. It's either going to be proportional or linear. Look at that, right through 0, 0. It's proportional with the exception of that data point, right? We don't want that data point to be on because it's clearly it's a mistake, right? Again, that fell off the wheel, so that data is bad data. Okay, so now the question is what can I figure from this information? I clearly have a pattern. I've got a slope. If you look at the units for the slope, right, I've got meters per second squared over newtons, right? Rise over run. So the y units divided by the x units gives me meters per second squared per newton. Okay? I'm going to talk about them in a second. That's kind of hard to make sense of those units. So I'm going to do that in the second video on my iPad.